or 2. And just to refresh your memories on how we get this textbook, let me go back here and type in Google search calculus, and I put one of the authors, Edwards, and then PDF next to it. So when you hit search, the choice number 1 pops up. So choice number 1 is what we really need in here. So you can select it and you will get this textbook that we utilize for this class. The textbook has a nice feature in it, the table of derivatives and antiderivatives, the integrals. So it turns out that most of the time people check if we have particular antiderivative as a derivative of the function. So I guess the fastest way to see this is just to take derivative. Like, for example, last time we used a little formula here that said if you take the antiderivative of x to the power of n dx, so that's how we write antiderivative. So we put the integral sign and we also have to put dx. So without dx, it makes no sense. So we got this expression in here. It's just like if you put a square root. So they will say, okay, Alex, square root of what? I just want a square root. Same here, if you just want an integral of 2x. But the question is, what are you integrating with respect to? With x, with respect to y, z? So it's going to give you different answers. That's why you need to have always that dx. That's important. So that's how it's defined. And the formula we had was x to the power of n plus 1. So that's probably the most useful formula in calculus, the power rule for antiderivatives, and of course, plus the constant. So how do I check that this is correct? Well, I go back and I use derivative of my result. So if I take the derivative of this expression, then I need to realize that derivative of constant is going to be 0. And that's actually what they should have here among the formulas. It's formula 5. I like to write derivative with just a prime, but you can go ddx, so you show that's a derivative with respect to x. So derivative of a constant c is 0. And then there is also a power rule for the derivatives that we utilize. It's right here, and we'll write it a little bit simpler. So u to the power of n has derivative such as a power 1 less, remember? And that power of n will be in front as a factor. And they actually proved this formula in the Calculus 1 class, just refreshing your memories. So analogously, when I differentiate that expression, then 1 over n plus 1 as a constant will stay outside. And then you're going to multiply it by the power. N plus 1 will now go on the ground, just like it happened with the power n. And then your x will be raised not to the power of n plus 1, but you're going to subtract 1. And then after you cancel a few things here, and to cancel is my favorite. I just love to cancel. I don't know why, it just feels good. So x to the power of n is remaining. 0 is gone, and you see that indeed, when you take the derivative of your antiderivative, you return back. So it's like a inverse operation. That's why they call antiderivatives. And that's how most of the time people check if they forgot the formula, if they differentiated or if they found antiderivative correct. Just take a derivative of it. And I guess that's a pretty neat and short approach that I think most people like. So formula or power rule for antiderivatives will be with us. You can see that first part of this little table deals with various derivatives. So I show you this because it's very useful to refer to it, and we will refer to it every once in a while. And then also there are formulas for antiderivatives that follow next to in the second part of this table on the very first pages of this textbook. They actually do have pretty much all we need here. And I know that you know for sure first formulas, but it's good to realize that derivative or antiderivative of tangent is ln of cosine with a negative. You don't have to memorize it. That's why I show you these formulas here. And if you take the antiderivative of secant, that's ln of secant plus tangent. Of course, you can just write this tangent as sine over cosine, then you will substitute cosine, and maybe I'll do it once when we hit one of the exercises like that. So I hope over the summer you did not forget everything from Calc 1 completely. So the other reason I try to show you this is just to make sure that you recognize when we have exercises such as antiderivative of cotangent. So there is a formula for that. Or secant and its friend cosecant. There is a formula for that, as well as secant squared and cosecant squared. So there are also formula for it. Secant tangent, also very popular. Well, the rest of them, people, well, we'll talk about a little later. But these first formulas, and of course, with sine and cosine, those are ones that we should definitely be aware of, and we will be. So when you look at them once, then you look at them once again. Another time, I hope you will start to feel that something familiar. And when you think it's familiar, then you can check out this bunch of formulas and it will give you a better feeling. So there is a group of formulas from trigonometry here that sometimes useful to do, to consider, and we will also a little later. So we're not going to very heavily use those, but some of them, like favorite, say, double angles formulas, those are ones that we gonna see every once in a while. And of course, Pythagorean theorem, I guess that's the key formulas for trigonometry class. I know that they don't look much at the last two, but if you rewrite tangent with sine over cosine and secant as 1 over cosine, then clear in denominators, you will get the original Pythagorean theorem identity, right? That is based on definition of sine and cosine. Do you remember what sine and cosine are? I think easiest way is to define them on the unit circle or circle with radius 1. So you produce the angle theta by starting at the origin and going to hit that unit circle. And then coordinates of this point on the unit circle we call as a cosine of theta and a sine of theta. And since circle has radius 1, then those sine and cosine cannot exceed 1. And of course, the point could be anywhere on the unit circle, depends on the angle. So sine and cosine may be negative, but they vary in between plus and minus 1. And that's something that we should also be aware of, because that's something that we're gonna also utilize in the exercises. Sine and cosine. Plus, when you get this definition of, so x coordinate of the point on the unit circle produced by the angle is going to be your value of cosine theta, and the y coordinate on the unit circle will be defined as a sine of theta. So I guess this definition is nice to be aware of, because that right away tells you that Pythagorean theorem, such as a sum of squares of sides, right? Like a squared, b squared, c squared. So you see this right triangle, and you right away see that this is a angle theta. So this is 1, this is a sine of theta, and this is cosine of theta, right? So we get a definition of sine, which is opposite divided by hypotenuse. That's another way to define sine, opposite over hypotenuse. And definition of cosine, which is going to be same as the length of adjacent side divided by, again, hypotenuse, right? And when you divide by 1, it's really same as adjacent side, but in any triangle, if you use similar triangles, you will actually have definition of sine and cosine this way. I'm not sure if they wrote it. Oh, here it is. So cosine and then sine. So it extends to triangle with any hypotenuse, not with hypotenuse 1, because you do similar triangle argument. So you have the quotient that hold the same result. So I hope you saw this before in trigonometry class. And again, it's good to be familiar with these ideas of adjacent hypotenuse, because eventually we will hit this in the exercises. The other formulas are not as popular, so I'm not gonna look at them in very details, but I would recommend that you have these formulas somewhere, maybe hang or just place in the area where you see them once in a while, because we should be familiar with them. So with this free textbook that was found online, and I can, of course, put this link once again for just in case here in a Zoom chat for you. So you can, I hope, save it if you didn't save it as of yet. So you can save it somewhere on the hard drive. So we're gonna use it for various in-class demonstrations as well as for out-of-class exercises. And we start with first section of chapter 7 with section 7.1. So let me clean this mess I produced when got so excited about refreshing on some trigonometry and other stuff. So the fast way to clean it is just to stop share the screen and then to share it once again, so it's all nice and clear. 7.1. I barely started to talk about it. I didn't ask you to do any homework from it, so we'll do it together right now. And for this class, exercises have tendency to be pretty tedious sometimes, because the idea is pretty straightforward, but if you get a little bit worse numbers, it may end up being a very lengthy and kind of unpleasant exercise. Of course, on the tests, I'll try to avoid giving you some nasty problems with lengthy solutions. And well, I hope you will see that. So anyways, page 448 is where we were. To get there, I'll add like 25 or so. So it'll be like 470 or some in that area approximately. So we'll get to chapter 7 this way. So I looked at the main idea, main formula in the section that said how to find the origin in between of two curves. And the way to find the origin is, first of all, to identify which one is the upper and which one was the lower curve. And once you set the area in between of these two curves as a difference between upper, which happens to be function f in this case, and looks like f of x here is 2 minus x squared. So you always subtract from the upper the lower. When you say, Alex, what's going to happen if I subtract them once, vice versa? Well, the answer will be negative. So area is not negative. So if you subtract vice versa from lower the upper, area will be negative, and that should tell you right away that you misplaced upper and lower, so you should switch them backwards. So it's not a big deal, I guess, but you want to be careful. That's the message. Now, to find this area of origin, I need to see where it ends and where it starts with respect to x, because I integrate here function of variable letter x. So in this class, we'll pay close attention if we integrate with respect to x or not. I say, what does that mean? Well, I'll show you another example that will integrate with respect to y. So from -2, my x starts and ends at value of 1, right? So we integrate from -2 to +1. I guess that's the key part of this exercise, because once you set this up, well, I'm sure you know how to integrate, how to find definite integral, how to use fundamental theorem of calculus once. Last time I went through this once, and if you start to use some negative numbers, you may see that it'll be a little bit more tedious. Now one can say, what are you doing here in this solution? Well, looks like they were not given the intersection of these two curves. Please notice, if you're not given the actual graph, because they just gave two functions in the exercise, then you should see when they intersect each other. And these points of intersection will actually give you limits. So to find points of intersection, you set one curve equal to the other curve, and this enables you to find values of x where y's are the same, y coordinates, because these are actually y's, right? So when y is same for both, then the x is found, and those be exactly values -2 and 1. So that's a standard procedure, but it's not that obvious. So I would highly recommend one to think about it and maybe redo another exercise like that, because now here I can find something that is less pleasant, like example number 4. I want to just take a look at their pictures to give you an idea of really process that we're gonna go through. Of course, I'll do some exercise after that, but the point is that sometimes those intersections might switch the order of your curves. So what I'm talking about here is example 4, where the upper curve switches with the lower curve. Look at this. They actually have to be very careful and to break this into two different integrals. So there is one area here from -2 to 0, and that area they called as capital A, right? So that area will have the upper curve, which is function g, looks like, and the lower curve, which is function f. I say, Alex, g is here down below. Yes, it is, but for that piece, g is above. So upper will be g. So first piece goes from -2 to 0, and the function which is above will be oh, actually that's a cubic parabola, right? Because that wiggle means cubic. So the upper, I should be careful, will be that 3x squared minus 3x cubed minus x squared minus 10x. And then the lower that I have to subtract from the upper will be my function g, which is negative x squared plus 2x. Negative x squared plus 2x. And that will give you some positive area. When you carefully subtract, do this algebra, and then technically the process is just tedious and it takes time, and you can see what they produce. They got number 24. But then for the second region, looks like there is another area that starts at 0 and looks like goes up to 2. They have another piece. Do they do this? Actually, I don't think they do this. See, for some reason, they just found one area. So maybe I can do this for you then, because they somehow did not bother to complete this. So the other piece will be from 0 to 2, but now it looks like it'd be a switch in these curves. X squared plus 2x will be on the top. Let's see, what are you talking about? Well, look at this. That's my parabola piece, that x squared with negative sign, so it opens down. And then the other, which is 3x cubed minus x squared and minus 10x, has to be subtracted from it. And they found that this value is 24, and looking at that, their node, they found that the other value is also going to be 24. So the actual sum of those two areas, the total pink area, will be 24 plus 24, so that'd be 48. And the message of this exercise is, if you didn't split this into two, so if you integrated it from -2 to +2, if you didn't notice that these two curves switch their positions, upper and lower, at the origin, then the result will be 0. That's what they're saying, because one of the areas will be positive 24 and the other will be negative 24. So instead of adding these areas, they would be actually subtracted, and you would get the wrong answer because didn't pay attention which one is upper, which one is lower. So if curves intersect more than twice, if there is another point of intersection in between, then one needs to be very careful and break this into pieces, because otherwise one area will come with a plus sign and the other with a minus sign, just like we already noticed. If you switch upper and lower, the result is negative. So instead of adding, they will be subtracted and you will get incorrect answer. So point is, one needs to graph those curves. And of course, one needs to solve for x, and that's what they did here in the first step. So it looks like these problems, they do take a little time to be done. So well, we'll do one. I just wanted to show you one more observation by looking at example 5 here. So please notice that in example 5, the curves will also switch their roles of being upper and lower. If you integrate with respect to variable letter x here, then you're gonna have to get the split into two pieces, because here the upper is gonna be the line and the lower will be part of this parabola. And then for the second piece, the upper will be another part of parabola and the lower will be another part of parabola. And that's very inconvenient to integrate, because you're going to have to do two calculations, right? There are two separate areas, just like in the previous exercise. So what they do is they look at the upper with respect to x-axis. So if you look from the left to the right, the upper one will be a parabola, and the lower will be the line. So when you integrate this way, you're going to have the upper, which is square root from whatever 3 minus x, and then you subtract the lower, which is x minus 1, and you're going to integrate now with respect to y variable, and looks like your y's, now you're looking at the second coordinates, will vary from -2 to +1. So you go here, dy. How about that? I say, wait a second, Alex, if you integrate it with respect to y, then you probably should write those functions as not y of x, but x of y, because otherwise you won't be able to integrate. You see what I'm saying? Because your variable needs to be a y, because you're integrating with respect to y coordinates, right? With respect to second coordinates. So you see how y varies from -2 to +1. So that's why I need to pull out x from here. So I'm going to have y plus 1 instead of x. So instead of this one, I put y plus 1. You see, if you go dy, then you need to pull out y. And analogously, from the other one, I will pull out x by first squaring both sides. So it'll be y squared. So it'll be just 3 minus x here. And then probably bring x over and have 3 minus y squared on the right. So instead of this square root, which is not very pleasant to calculate, well, you can just do simple substitution, right? And they'll get 3 minus y squared. And well, that'd be pretty straightforward. Again, the favorite power rule for antiderivatives will be utilized and finished with this exercise. And I think that's what they did. Or they even did it twice. It looks like they even did it -2. You see, they did it twice. So first way they did with respect to x variable, and they had to split it into 2 because first region, just like you already saw, was that piece, right? From -1 to +2. And then the second region was here that picks up at 2 and goes to 3. So they had to split it into 2, and that's quite a bit of work. But then, did they do it with respect to y? They did not. Well, let me do this with respect to y. And you see that the answer should be the same, right? So how do I integrate this with respect to y? So I get one integral to find rather than 2, and looks like I'm going to have minus y squared, and then minus y, and then -1 and 3 will be +2. I say, what are you doing? Well, I distributed the parentheses, so minus makes both of these negatives. So I've just rearranged these terms from the larger power of y down to the lowest, which is 2. And then I use the power rule to find antiderivative. So it'll be like minus y cubed over 3, right? For first power of y will be y squared over 2. For 2 will be just 2 times x, because derivative of 2x is going to be equal to 2. And then we need to replace -2 and 1 instead of our limits. So when I put -2, it's going to look like, see, now it's a tedious part. -2 cubed. It's not that bad though, because there are way worse exercises. If you put some fractions, I think last time I told you, if you want to put some fractions, it'd be nasty arithmetic that you're going to spend probably half an hour messing with, and then will be hard to actually oh, I should have put 1. That's okay. I put with negative sign. So we get a 2 times -2. It's been too long of the summary, I guess. So minus, and then with a plus sign will be the same thing, but now I put 1 here in the parentheses. So we get this 1 squared over 2 plus 2 times 1. You see that now it's kind of easy to make a little bit of a mistake. So we can see that common denominator looks like is 6. So I multiply this by 2 and this by 2 and this by 3 and this by 3, right? And same here. So this by 2 and this by 2 and that by 3 and that one by 3. So let's see what we have now. So looks like 2 minuses disappear, and then it's a -2 cube. So it's still going to be minus. So -2 cube, which is going to be -8 and 2. That's 16 over 6. I say, don't you reduce it? Well, I want to get same denominator. That's why I put this together. So now again, another minus and another minus inside. So they disappear. It's plus. So it'll be 4 times 3, 12 over 6 plus 12 over 6. So far, I'm not touching this number. Maybe I'm not going to need it. So it's a -4 with another minus. So it's +4. So I calculated the first piece, and then second piece will be -1 times 2 is 2, 6, right? And then -3 over 6. And finally, something positive, like number 2. See, I need to get a little room for this. So let me see how many 6s I have. 16 and 12, so it's -4, and then -5, it's -9, 6. So maybe I'll continue here. -9, 6, and add it with 2 and 4, which is 6, right? Add it with 6. So when I subtract these two, yes, I do get the positive result. So from 6, I subtract 9, 6, which is actually same as 3 halves. So 6 minus 1 is going to be 5, and then it's like 4.5, something like that. Oh, I got lucky at this time. Same answer as they produced, but much faster because there was only one integration done. And I guess the message of this section, as well as of this class, that sometimes it's much more convenient to integrate with respect to y variable than with respect to x variable, simply because you get to take only one antiderivative instead of two. Plus, when they did the solution for the exercise in example 5, you notice that they had to go through substitution, right? That 3 minus x, they had to replace with new variables. So it's like a little substitution. Some people do it mentally, but still the limits of integration change. So it's still a mess. And so it's like twice more work compared to what is done when you integrate with respect to y. And all you have to do is, instead of upper and lower, just use right and left curves, basically. That's all it is. And of course, to rewrite your functions by pulling out x rather than with y function of x, so you pull out x, just like that. So that's something interesting. That looks like I got lucky, I got the same answer, because sometimes you do all this and lose one of these little signs, and the answer is not the same, and that, well, gives you some unpleasant feelings. So
sorry to interrupt, and I apologize that I didn't interrupt a little sooner, because now I'm going to ask you to go back. Can you go back just for a second
Sure.
to that example? Thank you.
Sure, that's good that you have a question. Thank you, no worry. That's good. Yes. please.
Okay, so it's probably a very dumb question, but I don't quite understand. So I understood the upper versus lower by like position on the coordinates, right?
Uh-huh.
So I was okay up until this one, and I'm not exactly understanding why it's considered to switch at 2, because it looks like that darker line is still above the other in the shaded region. So can you just explain what constitutes the switch from upper to lower there?
Well, actually, if you rotated this by 90 degrees, then your x-axis will go here and y-axis will go there, looks like, right? If you rotate it. So your values will look like on the y-axis, so it's -2 intersecting 1, something like that. So the point of the story is that your region, the parabola, and then the line, it's kind of hard to put, I shouldn't put this. So the idea is to look at it from the left to the right, see? So if you rotate it like that, then that'd be your upper,
Right.
and that'd be the lower.
Yeah, on the when it's in the Y, when we're looking at it in terms of Y, that makes perfect sense to me. I guess I just get confused why when we're looking at it in terms of X, it's switching, because to me, it looks like even in terms of X, the gray line is still below it, except for in the area that's not shaded.
So you can perfectly do it with respect to X, but the you see the upper is here, but then the upper changes for the
Well,
other
that's what I
piece.
don't understand. How do you know the upper changes? Because that still looks like it's below the darker line, so I just don't get that part.
Well, this is the region you need to find.
Mm-hmm.
So this region looks like that.
Okay.
So this region actually starts at 2, right? Because that's X coordinate, and ends at 3. So this is 2, and this is 3 with respect to X. But your upper curve will be here. That goes from level of 2 to level of 3.
Okay.
That's the upper. So
Oh, okay. I get it now.
used to be line, but now
Yes, I see what's happening.
it
Thank
changed to
you.
this, the upper change. And that's why they have to have 2 different integrals, because notice that integration, integrand is not the same.
Right.
It's not the same. It is doable, but there's way more work. That's the message. That's way
Okay,
more work.
I get it.
But that's great that you asked this question. I'm sure that other people in class will also have this question. When you start doing it by hand, yeah, you're wondering what is going on. It seems that, but yeah, this little blue piece is hiding here from us.
Okay.
Nasty
Thank
little blue piece. Yes, yes. Thank you. That's very, very good question. So yeah, so and that happens quite often that this region is not designed with 2 curves, but looks like with 3 curves with respect to X. And by doing this integration with respect to Y, we've got only 2 curves, the parabola and the line. But with respect to Y, so we have to look from left to right or rotate it a little bit. And well, I guess that makes it shorter. In fact, not just because of that, because next section, we're going to do rotation around x-axis or around y-axis to get 3-dimensional. And there you will have no choice but to get this little integration with respect to y. We'll see that. Also, I guess another kind of unpleasant part was to rewrite this with functions with x on one side. So you had to do all this little algebraic. Well, it's not hard, of course, but there are lots of little steps in the exercise. So I would highly recommend you to try to redo exact same problem over weekend if you feel like it, because, and don't look at what I did, just try your own setting and see how that works. And because this is one of those exercises that given people a bit of a harder time. So anyways, sometimes people notice, like in problem 5, for example, so I just scroll down to the end of the section to the exercises. So the question will be, Alex, if you're saying that these exercises are so tedious, do I really have to do so many of them? Because that's a torture. And I know it. So I would say that you should try one exercise from each group here on the first page of section 7.1. I think we'll rarely go to the second pages because, well, there'll be just very lengthy exercises and we'll be stuck with them then for a few class meetings because there are really lots of detailed problems. So if someone is interested in doing something more detailed, then you can definitely do some problems from the next page as well. But I would say the problems that have the graphing calculator symbol, you don't have to worry about. So I would say this entire group could be skipped because sometimes they do put quite challenging problems in the textbook. So just do problems from the first page. And again, you don't have to really do so many exercises because it's going to end up with you just integrating again and again and doing pretty much same thing. But all I care about is which curve is on the top, which curve is on the bottom. Because once you set this integrand, then it's pretty much nothing that you have to do different with the other problems. It's usually the power rule. Look at all of these polynomials. They're all powers of x. So that's the only one that is a little bit different. So that's one that we may try to do. But let me try first 5. So I can do one exercise in this group. And I think a neat observation will be that this area seems to be exactly the same as that area down below, right? Why is that? Well, because this is the odd function. Looks like this is cubic parabola, 3x cubed minus 3x, odd function. So it's all symmetric through the origin. So that region is also symmetric. So if you rotate by 180, you will get the same thing. So I would say it's enough to get twice the area from either -1 to 0, so that little piece here, or from 0 to 1. But from -1 to 0, you just integrate your parabola 3x squared, x cubed, sorry, minus x, subtract 0 because that's your lower curve dx. And that'd be a pretty straightforward exercise, but then you just double it. Because if you don't notice it, well, you'll calculate the same thing once again, but with opposite sign for the second piece, and you will get the same exact answer. But I guess this observation will save you from this. And probably exact same observation you can make here because that looks pretty symmetric also. When it's Alex, you have to prove it. Well, notice it's all shifted by 1, right? Because if it's x minus 1 in the parentheses, then you can think of x cubed, which is symmetric through the origin as well. So it's really shifted by 1 unit to the right. So these two areas are also same. So you, instead of calculating 2 integrals, you just do it once and then double. So I think that's interesting to observe. In fact, lots of times when you take, if you ever heard word GRE, graduate record exam, if you want to go for master's program, they like to put this kind of exercises. So if people do it just directly, they waste so much time compared to just observing and noticing, oh, that's twice the area. And sometimes you get the answer right away without doing all this calculation of your integrals by just looking at the pictures. So you save time, and that way you can do more problems. Because usually they put so many exercises on mathematical part of that exam that nobody can do all of them. Usually people do like 30-40%, that's average. But if you do a little bit faster, then you get like 50-60%. That way you definitely get the highest scores ever. So anyways, these are interesting things to notice. Instead of just jumping and doing problem, just look at it first. Maybe you'll get some great ideas. So anyways, as promised, let me do one exercise with a little bit less pleasantly looking integrals, but I think the substitution x minus 1 is not really that bad. So let me do 34. Maybe that one is not very nice looking, right? Let me try 34 and see what they want. So sketch the region bounded by the graphs and then find the area. So what about such exercise as 34? So how can I possibly do this area finding? Because technically one would say, okay, so maybe it's just one function and the other, but which one is higher, which one is lower? And that's the question, right? And when you try to sketch this region, it's probably going to take you forever to do, right? But what I can notice that this is the odd function. Why is it odd function? Well, it's symmetric through the origin, because if you look at f of minus x, it's the same as negative in front of f of x. That's the definition of odd function. So if you put minus y here and there, then you have denominator y squared, so it cancels, but the numerator minus y stays, so it will take it out. So it is indeed the odd function. And that's why, since it's odd function, just like we observed with, let's say, cubic parabola, the regions will be the same. So I don't have to find, say, both of them, but just the one that I will multiply by 2 but double it, right? When you say, Alex, but still it's a function of y, it's not a function of x you found. So how can I actually deal with this? Well, let's see. So they say y is equal to 3. So y is 3. We're gonna, well, let me get x equals to 3 first. So x is 3 will be someplace here. So like cut off. So if they be functions of x, because if functions of y, I just switch x and y and get the result right away. Maybe I need to get some room for this. I think that'd be a good idea, right? I think I selected something that I probably shouldn't have selected, but I wanted to get something different than all of these, because these are all power rules and that one will be substitution. So let me share a board. And write this functions. So let's see what they are. So one of them is x, because f of y is x. It's y over square root 16 minus y squared. Okay. Of course, the fastest way is just to get the graphing calculator and graph it for yourself, because otherwise you'll be stuck with this graphing for a while. So another one, so it's x is equal to 0. And the third one is going to be y is equal to 3. That's the third one, right? So since we used to graph functions with respect to variable x, so if you graph y is equal to x over a square root from 16 minus x squared, so that'd be one of those functions, and then y is equal to 0, and then x is equal to 3. I guess that'd be pretty much same region, if you just switch X and Y in here, but it will look like not along Y-axis, but along X-axis, right? So that might be a little bit more familiar to us for graphing. So I can start with graphing it like that. So Y is equal to 0 is my favorite X-axis. I know for sure how that looks like. It's here, right? Y is equal to 0. Of course, X equal to 0, that will be like a Y-axis then. So they switch. Now X is 3, that's a cut done right here. So X is equal to 3. And then it looks like 16 minus X squared. That's something that has quite a tough domain, because the main here is 16 minus X squared that needs to be non-negative. Otherwise, we get something that will be irrational, right? Because X squared needs to be less than or equal to 16. So X has to be in between minus and plus 4. And since it's odd function, then somehow it's gonna be going like that through point 0, and then similarly like that. I just making it up because I'm not sure exactly how it looks like, but the idea is that at point plus 4 and minus 4, actually we hit back our axis. So somehow it looks like that. So the question is, what do I need to find in this case? And the answer is this area, and then the area here, because point 4 is going to be right there. And of course, you can do it all with respect to Y variable, so the picture will rotate by 90 degrees, but it's going to be the same answer. So it's more convenient for us to graph, I guess, with respect to X anyways. So there'll be two areas. Sometimes we will say that's area 1, and that's the area 2. I thought I will be able to use the fact that it's odd function, so I will just find one area and double it, but this line X equals to 3 is designed to give me a little bit of a hard time, right? So these are points like -4 and a 4 and a 3 here. So for area 1, I'm going to be integrating it from -4 to 0. And for area 2, I will be integrating it from 0 to +3, not 4. But the expression of integration will be the same. So it looks like in the first case, I'm going to subtract from 0 this fraction x, and this is 16 minus x squared, something like that. And we can put 0 on the top. The upper is 0. And then for the other part, it will be the same type of integration, but vice versa. So you subtract 0 from that. So technically, you don't have to take antiderivative 2 times. You could just do it once, but then there'd be quite tedious plugging in. Well, actually, not really, because 0 will be your little friend. So again, the reason I selected this problem is because to take the antiderivative, we should use a substitution, right? So I replace, let's say, whatever's inside the square root with a u. When you say, Alex, why did you do that? Well, because that's a natural substitution. Whatever is in denominator or whatever is inside the square root, you always try to replace with a variable letter u. And when you take the derivative of the left side, it's going to be 2x, and the right side will be du over dx, right? Derivative with respect to x, and then I can multiply by dx both sides. I say, why you do this? Well, just to refresh your memories on why we attach dx with the x part and du with u part, because we actually clear this dx. So it looks like -2 is on the way, and then I can say that x dx is the same as du over -2. Okay. So now I'm ready to do the substitution. Remember how we usually doing it? So numerator x dx, I'm replacing with du over -2. I just put it the way it is. I don't want to do any algebra in my head because that way I can make a mistake. I don't want to make a mistake. So, and then what's left, let me put the same color, the brown. It's 1 over square root, and my substitution is right there. So instead of expression inside the square root, I just put letter U. So we have perfectly nice integrand to take. We use the power rule for it, remember? -1/2 goes out, and this will be U to the power of -1/2. See, all of these antiderivatives end up being the power rule problems after you substitute. Well, not all, but pretty much all of them. So you end up with a half in front, and then U will be raised to the power of, I need to add 1. Remember the formula? So I have to add 1 with a half. So it'll be just a half done. So it'd be U to the power of 1/2. I don't want to write the square root because I will, again, do too much in my head, and that's the last thing I want to do. So 1/2 will cancel, just end up with a negative sign that still remains, and it'll be a negative square root from U. And then we go with the original variable, which is going to be 16 minus x squared. And then I can do the substitution of 0 and 3, just like that, and get something like upper is 3. So I'm going to have a square root from 16 minus 3 squared, and the lower will be 0. So I have to subtract from it, right? That's a 0. I wrote it. It looks like infinity. No, it's 0. No infinity. So I subtract from it negative square root from 16 minus 0 squared. Okay, so 3 squared is going to be a 9, subtract from 16, so it's a minus square root 7, plus square root 16 is 4. So it looks like it is something positive. It doesn't look very friendly though, but well, you'll keep the answer with a square root. And the point of story that now for the other piece, it'll be exact same thing with this substitution, but you're going to end up with not a plus like we had here. So we ended up eventually with a expression that looked like that. But since it's exact same thing, but that'd be an expression that looks like 16 minus x squared, but with a plus sign, with the opposite sign. Because again, here we have a minus in front of this, and there we have a plus. When I say, Alex, maybe enough. Yeah, enough. So it's plus. We don't write it. But the point is, we integrate exact same thing, but one is positive, the other is negative. So after we went through all the integration process, I end up with one expression and the other with opposite sign. But here we go -4 to 0, and then you plug in 0, you plug in -4. Looks like at -4 we're going to get 0, so at 0 it's going to be just a 4, right? And that's it. So that's one area. So this is 4. The other area is 4 minus square root 7. So when you add these two areas, you should get 8 minus square root 7. But that's too much. Do you see? This is really too much. It's so tedious. That's why I don't want you to mess with these problems a lot. Maybe you do one, and that's good enough. Because otherwise you'll be stuck the whole weekend to just keep on integrating and substituting. But I think if you can just redo the same problem again, maybe sometime tomorrow morning is too much for tonight, that'd be just perfectly fine. Again, the good thing is it's all being recorded, and I will, of course, email you a recording sometime tomorrow. And, well, there is not much in it. The only thing we learn is upper and lower, right? That's it. And we subtract them. And of course, you can create tons and tons of exercises, just put various substitutions and stuff. But the whole idea is which one is upper and which one is lower. So I'd like to ask you a little quiz exercise. So you will also tell me which one is upper curve and which one is lower. when you're gonna integrate. So let me actually,
Before you do that, I
yes,
have a question for this
sure.
problem. How did you get the graph for the equations?
That's a very good question. The only idea I used that this is the odd function. So I made up some kind of odd function. So one piece. So I don't really care what the graph is. It's something that has 0 when x is 0, definitely, right? When you put 0 for x, that numerator is 0, so it has to go through the origin. And then at point 4, we going to have, oh, I actually had to be careful because it's undefined at point 4, right?
Yeah.
Root of 0, so it's undefined. So yeah, my graph is not correct. It should be going somehow differently. You're absolutely right. See, I should have been a little bit more careful. And then there'll be indefinite integrals. So I'm not sure then we can actually integrate it, because if we have the -4 plugged in here, it'll be 0. So we're going to have the asymptotes, right? And that's something that I think we're going to do in the very last section of this chapter, this type of integrations. We didn't learn it yet.
With x equaling 3 though being one of the lines, wouldn't it just be
Yeah.
that little section right there?
Yeah, with 3 will be fine, but see here, we actually have the asymptote. Yes, that's a very good hint that you just gave me. So this is not going to be really that, because I need to go with limits, so it'll be much nastier than I try to make it be. But I guess my main point was to show you that you can integrate expressions like this with substitution, to refresh substitution. But yes, this kind of exercise, maybe we can hold on to till very last section of this chapter 7. It's called improper integral, actually, because with asymptote, I had to take a limit and then find a limit, but we didn't do it. Probably the answer will be something similar to it, but that's something that I really have to do a little bit differently. But again, I made up the graph and I solve it. If the graph looked like that, it'd be fine. But you're right. The denominator is 0. It's not really that simple.
Okay.
If that be numerator, then it will be fine. But it's in denominator. That's what I didn't notice. But that's very good. See, those little observations make you actually realize what is going on much better. And that's great. So anyways, it's all recorded, so I'm gonna go back to the textbook. So let me go back here. And yeah, they shouldn't really give any areas that end up being improper integral. And this is exercise 34 that doesn't even have the answer for us. And I think that's the reason why they actually did it to us, because they probably never solved this exercise, because they should put it in later section, because that's not from here. But anyways, so the question is, what is upper and what is lower? Looks like that's the key part in all of the exercises, right? And I will ask you for the exercise number. So I'd like you to do a little quiz. How to do quiz? First of all is don't hurry. Don't hurry means don't send your answer in a chat. So we have a Zoom chat, right? Did you know there's chat? And that's where I put the textbook. So you can send to everyone whatever you like, but don't send it to everyone. Send it only to Alex. And for exercise number 1, tell me which one is upper curve. So all you have to do is just only to Alex, tell me, is y1 or y2? Which one is upper curve if you start to set the integration? So for quizzes, I usually put some pretty straightforward questions. So you just put the answer in the Zoom chat, and after that you can relax, but please don't hurry. Don't hurry, because